So now we're coming at the final part of this module about zero knowledge. I want to show you a protocol for showing that the Boolean circuit can be satisfied. It should be obvious that in that case the circuit is knowing to both the prover and the verifier. I'm going to give you this protocol only by example. We will follow the same structure as that we had before. So here, and it's a toy example also. So here I have a toy version of a Boolean circuit. So we can see here we have an AND gate, we have an OR gate, we have an XOR gate, we have an AND gate, and we also do sometimes complementation on the wires, right? So we also have connecting wires, and as you can see, the end result of this computation is 1. Maybe I should, it's 1 0, which is here is the 1 is the first wire, 0 is the second wire. So this is the row of the gate of the table that's been selected, and we have all these connections. So this is the Boolean circuit, and we also see that, well, when we run it with input 1 0 1, the end result is 1. So what we want to do now is we want to create an alternative version of the circuit, which will hide all the information about the circuit, and that will nevertheless convince the verifier that this circuit can be satisfied. Of course, it's a small example, so that in that case it's not difficult to find. But imagine a very large Boolean circuit using the same ideas as presented here. So first, I'm going to explain to you how we are going to create a permuted instance of a gate. So this, I believe, is the first gate. So what we're going to do, we are going to apply a permutation to all the rows. This is one thing. And the other thing is that we are, so this is the permutation. We also sometimes flip the values on a wire. And so when you flip a value on a wire, you need to flip the value in the column. And by the way, if you flip it on a wire, you also need to flip it, well, it's not shown here, but in the gate that's the original gate here. So this is what we are going to do. So this is, we're going to flip with the 1. In this gate, there is no change because it's exclusive or with 0. And this will lead us to, we're going to flip, see here, we flip the third column also, which is a 1. And so this will give us the final permuted gate of the first gate of this circuit. And what we're going to do, we're going to repeat this on each of the gates. So this you can see here. You can see, so the input, in this case, the input gates are, or they are permuted here, right? And you can, the wires, I mean, so this is the first wire is flipped, the second wire is flipped, the third wire is the same. Here also you can see whether the wires are flipped or not. And so flipping the wires means that the column are inverted, and apart from that we are permuting columns. So this now is the permuted instance of the circuit, and what the prover is going to do is she's going to commit to each of the values in these gates, in these tables, and she's going to send this to the verifier. Now the verifier is going to flip a coin, and there are two possibilities. The first possibility is that the challenge is a 0, and in that case the proof is going to open all the commitments and it's going to show that the premuted instance was a faithful creation of the original instance. Oh, this is the outline. I forgot I had this slide here. So this is the outline. I commit to the permuted instance. There's going to be a challenge, 0 or 1. The prover, if it's 1, it opens all the commitment and shows it's a faithful representation of the original. Or when it's 1, it will open selectively some commitments, which is very similar to the Hamiltonian circuit problem, in which case we were shown the existence of a circuit. Here it's going to show that the alternative instance has a satisfying assignment. So this is shown in this diagram here. The verifier, the prover is going to open only these rows, and the verifier must show that the consistency between the rows. Of course, this cannot be shown because these are the inputs. But for instance, if there is a 1 here and there is a wire here, then there should be a 1 here. If there is a 1 here and there is a wire here, there should be a 1 here. In this case, there's a 1 here, but there's a not on the wire, so this returns in a 0. And of course, we need to see the final value, which is 1. So this is a way, a very simple protocol to show that a Boolean circuit has a satisfying assignment, which is of course very interesting because it's a way also of showing that satisfiability, which is an NP-complete problem, can be implemented using this approach. So this is the end of module 3. Where are we? Well, I want to remind you that we are sort of taking this term zero knowledge SNARK and analyzing it. So zero knowledge was explained in this module. Remember that there are SNARKs that are not zero knowledge. People do not always care about the privacy. Sometimes they care about the proof aspect, but not about the privacy aspect. So the S stands for succinct. And by the way, this is the problem of the protocol that I just showed you, because if you have a computation, and then you take an ordinary computation, then the Boolean circuit that represented is huge. And so the proof is not going to be succinct. So this is the major disadvantage of what we just saw. It shows that in theory, any computation can be shown in zero knowledge, but it's not very practical. So the succinctness is an important aspect in this whole context, and this is what we're going to address in the next module. The non-interactive part, the N, I've explained it exhaustively in module 2, and I mentioned it briefly in this module. The argument, it's the A and the R actually. I explained you the argument and the proof. They are two different settings about the relative computational powers of the prover and the verifier. And the K of knowledge was explained in module 2. So this is where we are. What is remaining in the next modules is the issue of succinctness.